Good afternoon, everyone. I'm Jim Gregory, professor and chair of the Department of Mechanical and Aerospace Engineering. And it's a pleasure to welcome you to the next installation of the Monte and Usha Ahuja Distinguished Lecture Series. The lecture series is named after the Ahujas, who have generously endowed this lecture series. Their philanthropic support to inspire the next generation of graduate students in mechanical engineering, and to create this vibrant environment where we can hear from eminent speakers, distinguished guests on a regular basis, to exchange ideas, and to really the scholarly spirit of the university. This is at its best. So we're very thankful for the Ahuja's generosity in supporting this lecture series. And our goal here is to invite illustrious, distinguished guests or rising stars in the field to share their expertise, their wisdom, their scholarly insight, and contemporary topics in science and engineering, and hopefully inspiring the next generation, the graduate students who are with us here today to achieve their best and contribute to society in meaningful ways. So with that, we're delighted to host the next installation today, and thank you to Jack McNamara for organizing this visit. And Jack, the floor is yours to introduce our guest.
Thanks so much, Jim. So it's our pleasure to have with us Professor Earl Dowell, the William Holland Hall Professor, Pratt School of Engineering, Duke University. Professor Dowell received his BS degree from the University of Illinois and his SM and SciDoc degrees from the Massachusetts Institute of Technology. Before he came to Duke, he was Dean of the School of Engineering, before he came to Duke as Dean of the School of Engineering from 1983 to 1999, he taught at MIT and Princeton, and he has industrial experience with the Boeing Company. Professor Dowell is very special in that he has amazing breadth and depth, and this is reflected in his long lists of honors, awards, and contributions to the community. He's an elected member of the National Academy of Engineering, an honorary fellow of the American Institute of Aeronautics and Astronautics, a fellow of the American Academy of Mechanics and the American Society of Mechanical Engineers. He's served as vice president for publications and member of the executive committee of the board of directors of the AIAA, as a member of the United States Air Force Scientific Advisory Board, the Air Force Studies Board, the Aerospace Science and Engineering Board, and the Board on Army Science and Technology of the National Academies. He's also been a member of the AGARD NATO Advisory Panel, as president of the American Academy of Mechanics, as chair of the U.S. National Committee on Theoretical and Applied Mechanics. He's received many awards from AIAA. He's received the Structural Dynamics and Materials Award, the von Karman Lectureship, the Kirklope Trust Prize, and the Reed Aeronautics Award. From the ASME, he's received the Spirit of St. Louis Medal, the Dan Hertog Award, and the Lyapunov Medal. He's also received the Guggenheim Medal, which is awarded jointly by the AIAA, ASME, AHS, and SAE. His presentation today is titled Theoretical and Experimental Models for the Dynamic Interactions of a Flow Field and a Flexible Structure, where correlation is the key. As this webinar goes on, please type your questions in the Q&A as they come up. I'll read them out at the conclusion. And at that, I welcome our distinguished speaker. Thank you.
Jack, thank you so much. It's a pleasure to be with you. And Jim, thank you for your nice insights into this lecture series. I did go on the web to find out a bit about your donor, and it sounds like a very interesting fellow. I realize he's one of your alumni, and along with and a generous donor along with his wife. So this topic is the one that Jack mentioned. We're going to talk about fluid structure interaction, and correlation is the key, is the correlation between theory and experiments. So we'll have at it. So let's go. The subject is inherently multidisciplinary. We're going to talk about fluid structures, thermal fields, and nonlinearity. And dynamics is the intellectual glue that holds it all together. At least that's one perspective, and I think a useful perspective. Let me say a word about models to begin with, both for the fluid and the structure, to provide a context for what you'll see a little bit later. For those of you who work in fluids, you know there's a whole range of models that people use, starting with potential flow or classical aerodynamics, going through Euler, and then various versions of the Navier-Stokes models. But one point I would highlight for fluid structure interaction is that you can take any of these models and use the ideas of linear dynamical system theory, and for sufficiently small motions, construct in fairly efficient form a linear dynamic model, which sometimes, but not always, is particularly useful. And then particularly as Jack McNamara knows and others here today, there's been a whole raft of people and efforts to construct so-called reduced order models. And that means different things to different people. But in my context, it means that we're trying to find a way to take very large models of the fluid, large in terms of number of degrees of freedom, and break it down to something much smaller, but without losing any appreciable accuracy. And of course, that's easy to say, and as we all know, it's hard to do, but some success has been achieved. With respect to the structural models, we're much further along in terms of constructing reduced order models. We know certainly how to do it for linear models because we simply need to find the eigenmodes. And it turns out a modal representation works for structures as well, although I keep having people tell me that, gee, can that really work? And the answer is yes, it can. There are various nonlinearities that have been studied in the context of structures. Free play is something that's very important in practice and it's extensively studied in research as well. There are various geometric nonlinearities, and of course, you can look at beams, plates, shells, and other elements as well, including dry friction dampers. The role of finite element models. This may be mildly controversial, but in our experience, we normally use the finite element models to first find the eigenmodes, and then we use a modal representation when we couple that with some fluid model. And of course, it can also serve as a benchmark in terms of assessing how accurately the modal model is. So this talk in some ways is a not so subtle advertisement for the next edition of our book, A Modern Course in Neuroelasticity. So one new chapter is essentially a summary of some experiments we've done in fluid structure interaction over the last 10 or 20 years. And the second part of the talk is a new chapter on hypersonic fluid structure interaction. But this is the low speed part. We have a standard low speed tunnel at Duke, and we like to think we take this very ordinary tunnel and do, on occasion at least, some extraordinary things. And so that these are not a complete list, but it's 5 of the more interesting experiments we've done. And they're of current interest. We're going to look at a high aspect ratio wing model. There's a whole workshop being planned for the next SciTech meeting in January of 2022, led by Jennifer Hay at NASA, and with substantial contributions from Daniela Ravi at the Technion, a group at Imperial College, another group at DLR in Germany. And they're basically building a very flexible high aspect ratio wing model. And they're beginning their work on that. And I'll tell you a little bit about the work that we've done on that. A yaw plate model, we're going to use this as a context to look at both limit cycle oscillations of a wing, but also look at something that is sometimes called a flapping flag, which will at least touch briefly on the idea of energy harvesting. The free to roll model is because we were interested in the F-16, and the F-16 is a nice flutter machine, a limit cycle oscillation machine, and so we want to talk about that. Historically, free play was investigated at the Air Force Research Lab many years ago with an all movable tail model as item 4. And we have essentially replicated their experiment, but with a modern understanding of what the results mean. And then we've been very interested in buffet, which in our context is a large scale instability of the fluid alone, but once the fluid begins to oscillate in a limit cycle, then it does interesting things if it's in the vicinity of a flexible structure. So those are the 5 items we're going to touch on in the first half of the talk. So let's see what that is all about. In the second half of the talk, this is what we're doing currently. We are looking at global instabilities in transonic and hypersonic flow with some colleagues whose names are listed here. And we're particularly interested in shockwave boundary layer interaction, as so many people are. It's a hard problem, but a very fascinating one. We've been looking at limit cycle oscillations of cantilever structures. And we tell people who ask us why, we say it's a control surface, but it's fascinating all by itself. And then the last topic, third topic there is looking at clamp plates, which are typical of skin panels and high speed flight vehicles. And we're working with a whole raft of people who are doing experiments, and we'll show a correlation with one of them. So that's a preview of things to come. I'll start for the most part with pictures of experimental models, explain what that's all about, and then touch briefly on the corresponding theoretical computational model. So let's see if I can get my pointer working here. Yeah, I can. So here's our high aspect ratio wing. This is very similar to what Danielle Aravi is doing in a Technion wind tunnel at the moment. And it's cantilevered off the wall of our wind tunnel. It's a very flexible wing, high aspect ratio high. The span is large compared to the chord. We have something on the end so we can adjust the mass properties to either create or suppress oscillations. And if you take the blue cover off, this is what it looks like inside. So structurally, it's just a simple beam. But the interesting thing about this is for these very high aspect ratio, very flexible structures, the bending normal to the beam, but the bending in the plane of the beam are both very important. And we'll talk more about that in a moment. And then the twisting of the beam, of course, is important as well. So there are 3 global motions of interest. And let's see if I can get out of my pointer now. So let's look at the video. On the left, well, we have the wing in 2 different views. On the left, we're going to start at a low speed, essentially 0, and go up to 33 or so meters per second, which will take us into the oscillation. And then on the right, we'll start at that higher flow velocity and decrease it. We do this as an experiment because there's hysteresis in this model. And the hysteresis, we believe, is due to the separated flow and the stall aerodynamics. The dominant nonlinearity in terms of determining the amplitude of oscillation is actually in the structure, and I'll talk about that in just a moment. So we have both a structural nonlinearity and a fluid or aerodynamic nonlinearity in the picture. And there's hysteresis in the sense that when we go up, we reach a critical velocity, which up in flow velocity, we reach a critical velocity where the oscillation starts, and it continues as we increase the flow velocity further. But then when we come down in flow velocity, that oscillation persists well below the velocity it started when we were going up in flow velocity. So there's hysteresis. So let's start the video. And we'll start this one over here too, I hope. Oh, I didn't realize you were going to hear the wind tunnel. Well, I'm sorry about that. When I played it for myself, I didn't get the audio. Hope I didn't blow out your ears. So here's the computational modeling simulation. And for those of you who are into this sort of thing, there are a number of structural modes that are participating, but principally it's twisting, as you see, and the second bending mode, which actually has a node line about 2/3 of the way along the span. And then there's an in-plane deformation as well, but which is much smaller, but the strain energy and the potential energy of that motion is comparable to the other motions, and therefore you do really need to have it in your model. So let me do this. Yeah, let me show you some equations, and I won't go to this in detail, but I want to highlight something for you. V is the, let me get my pointer here if I can. Yeah, V is the displacement in the chordwise direction. W is the displacement normal to the wing, and phi is the twisting. And the underlying terms are the dominant nonlinearities in the system. And note that in the chordwise motion equation, which is what this is, it's the twisting and the other bending deflection that appear. And conversely, in this equation, which is the principal equation for the flapwise or transverse deflection, it's the twisting and the chordwise deflection that appears. And then in the twist equation, it's a product of W times V, and the primes denote derivative with respect to distance along the span. So these are really curvatures. And the intensity of the nonlinearity is the difference, delta EI, difference in the bending stiffness in one direction versus the other direction. This whole model was developed years ago for rotorcraft, because if you think of it, if you look at a rotor blade in a helicopter, it's a very high aspect ratio wing, which happens to rotate. And so now that high aspect ratio wings in fixed wing airplanes are back in vogue, we're using this same model again. And when I say we, I'm talking about the community. Okay, let's move on. Here's our version of a yawed plate. So I have a simple metallic aluminum panel, which is our flexible structure. The blue part is just a rigid, but hopefully aerodynamically streamlined holder, which clamps the plate along the edge where the two are attached. We can rotate this through several angles. If it's at 90 degrees, we call that the wing. If it's 0 degrees, we call that the flag. And then between, you can call the yaw wing or whatever you like. This one, the beta equals 0 or the flag configuration is the one that has the largest amplitude motion, as you'll see. So we call that the energy harvesting configuration. And you can survive wing LCO as well, although people have not always appreciated that, but we can see that when we look at the video. Oh, let me pause here. This is one example of the correlation between theory and experiment for the amplitude of the LCO versus flow velocity. And let me see if I can get my pointer going again. The theory are the open circles. The experiment are the dark points. There's a little bit of oscillation even below where the theory says the flutter and LCO begins, but that's just due to the turbulence in our wind tunnel. And we get a fairly good correlation between theory and experiment for the amplitude as a function of flow velocity, and also for the frequency. Here we see the frequency of these oscillations. So we're pretty happy about that. And now you can see for several values of beta, the wing, the yaw wing, if you like, and the flag. You can see how they go. I'm still not sure why you're getting the audio and I didn't, but I hope that doesn't destroy your hearing. The free to roll model was motivated by the F-16. It turns out that if you have something that looks like a fuselage up in the left-hand corner with the wing, that's the blue object. And if this pencil fuselage-like structure is free to roll, then in fact, this is more likely to flutter in an anti-symmetric mode than a symmetric mode. And we found that fascinating, as other people have. And so we thought we'd build a small model to show that. And here it is in a different view. And we correlated theory and experiment, which agrees fairly well. But again, let's look at the video. Here's the anti-symmetric case on the right. Note that the flow velocity is 16.7 meters per second, which is slightly smaller than the one on the left at 17.2. So if you do the experiment and you leave the fuselage free to roll, it's the anti-symmetric flutter that you'll see. But then, of course, we can lock out the roll motion, prevent it from happening, and then we can also measure the symmetric flutter at a slightly higher velocity. Another model that we've looked at over the years in several different forms and we continue to play with, in fact, we've had several investigators from other organizations come in and use this model for their own purposes. This is, let's see. Yeah, this is a wing model that we're going to mount from floor to ceiling. So it's a two-dimensional aerodynamic configuration, if you will. It's mounted on flexible supports, so it has both a translation or plunge degree of freedom and also can rotate about this point. So the main wing or airfoil has 2 degrees of freedom. And then we have a control surface on the back, and this is the hinge line for the control surface. And though it's hard to see in this picture, I'll show you a little more detail over here in an expanded view. There's a thin wire here, which is providing a spring connection from the control surface to the main wing. And it can move freely between two different points. And you see, if you look at that in more detail, you see it over here. So it's free to play between these 2 points. And then when it hits one point or the other, it bends and provides a linear spring. And this is all, something like this is almost inevitable in any flight vehicle with a control surface. So let's see what happens. Here's some, and it's a simple structure, right? With 3 degrees of freedom. It's low speed, so you could use low speed potential flow aerodynamics. And again, you can plot the response. There are 3 degrees of freedom, so we have 3 plots. We have 3 plots of response. This is the plunge. This is the flap or control surface rotation. This is the pitch of the main wing. And then this is the frequency of the oscillation. And there's some test data. And then there's a theory from both ourselves and Zona Technology and PC Chin, if you know PC. And the theory and the test line up. And what's interesting about that, well, there's several things that are interesting about this. One is that note that there's quite an interesting and fairly complex variation of the response with flow velocity. And if you look at the frequency in particular, we have a certain frequency that exists over a certain range where we're in a limit cycle oscillation. And then it turns out that limit cycle oscillation becomes unstable itself. The initial instability is here, but then the limit cycle persists and then it becomes unstable and we jump to yet a different frequency and a different limit cycle. And you can play with all sorts of parameters. You can suppress this oscillation by putting the wing at an angle of attack. In fact, sometimes practitioners say, well, we shouldn't worry about that. because wings are almost always at non-zero angle of attack. And if angle of attack is large compared to the free play range, you can show theoretically and experimentally that in fact this goes away. But then you have vertical tails with control surfaces as well, which is my counter argument to why we should still be looking at this. Okay. Now I mentioned there are two different limit cycle oscillations. One's at lower speed, that's the one on the left, and at a different limit cycle at a higher speed on the right. So we'll look at both. And we're going to start out looking at the spring, the free play spring, but then the film will pan back and you can see more of the motion. So let's do that. If you can, well, you can. I didn't realize I was going to have to speak over a wind tunnel. But if you were closely looking at the motion on your left, you saw that this was moving back, the main wing was moving back and forth a great deal. Whereas in this case, in this limit cycle, the main wing moves hardly at all and it's all the control surface. By the way, if you the range at let me go back one more. Yeah, the range over which we do our testing, it goes up to about 25 meters per second, and we stop there because the linear flutter speed, if there's no free play, is predicted to be at about 27 meters per second. So we didn't want to break our model. And that's why we stopped. Okay. I mentioned before that we actually constructed another free play model, which mimicked what the Air Force had done low those many years ago. In this case, the free play is at the root of this model, which is in this configuration mounted vertically in our wind tunnel. And that takes gravity out of the picture, of course. But we also wanted to look at what happens when we mount it horizontally. But let me show you briefly what happens here. That's a nice simple motion. But now if we look at it mounted horizontally, we have gravity in the picture. Gravity provides a static load, which induces, as it turns out, another nonlinearity in the system. So we have two competing nonlinearities. And now if you look at the motion, so there you actually have a chaotic oscillation, which is typical in our experience when you have at least two different nonlinear mechanisms competing for attention. The last thing I'll talk about in terms of this low speed array of experiments is an oscillating airfoil section in buffeting flow. And various people use different names to describe this. We're talking about a large scale fluid instability. So we already have a turbulent flow, for example, but now in certain Mach number angle of attack ranges in particular, we can have another global instability. We can bifurcate yet again, if you will. And in the airframe industry, this is usually called buffet. Sometimes a prop will install if a rigid body mode is involved. And the turbomachinery people tend to call it non-synchronous vibration. But whatever you call it, it's a large scale fluid instability. And here's our model again. Here's our airfoil, but if we rip off the cover, you can see various pressure traps, and then over on the left-hand side, you can see where the pressure traps are mounted on the upper and lower surface, because we want to measure the flow oscillations. In the initial experiment, the airfoil itself doesn't move, but the fluid is beating its heart out. And of course, fundamentally, this is similar to the von Karman vortex streak, behind a bluff body such as a cylinder and transverse flow. And there again is a characteristic screw hole number associated just with the flow oscillation. So let's see how this works. If you simply place this airfoil at any one of several angles of attack from 30 to 60 degrees, it has to be fairly high at low Mach numbers. It can be 3-4 degrees in transonic flow for the same basic physical phenomena. And you plot the buffeting frequency versus airspeed or versus Reynolds number, which is the same in this case. It's the usual linear variation. And then if you scale everything non-dimensionally and use the chord times the sine of the angle of attack, you can take all these data and make them into a single curve. So there is a screw hole number. And then the next thing you can do is you can start oscillating that airfoil at a given frequency. And now there are two competing frequencies. One is the frequency of the airfoil oscillation, and the other is the inherent frequency of the flow oscillation, even when the airfoil is not moving. And then you plot the amplitude of the airfoil motion versus the non-dimensional frequency ratio of the fluid to structural frequency or vice versa. And if that frequency ratio is sufficiently removed from one, either below or above, then you have two frequencies that you see in the flow, the inherent flow frequency plus the frequency of the airfoil motion, which is forcing the fluid at that frequency. But then if you're in a V-shaped area denoted by the green lines and the green data points, there, both the flow and the structure, of course, which is moving at a prescribed frequency, have the structural frequency. They have the prescribed motion frequency of the airfoil. This is called lock-in. And then if you place this airfoil on an elastic spring with a resonant frequency, which is in the same vicinity, you get very large motions indeed of the structure, which is its practical interest. And so this is, I won't bother to show this video, but it shows the airfoil oscillating and doing its thing. But I will point out that we also put a control surface on it, shown in the picture, a flap. And we took some data. And again, the flap frequency is now no longer a single frequency, it's broadband, it's chaotic, because again, we have two nonlinear mechanisms, the inherent nonlinear limit cycle of the flow interacting with the structural free play mechanism, which we put into that control surface. So now we're going to leap right through transonic flow and go into hypersonics. Actually, a fair amount of our current work is on transonics, but I had to make a choice, so we decided to go hypersonic for the last little bit. So let's go hypersonic. This work is, all of this work I've described has been done by a small army of people, and you'll see their names at the end. But this particular work, which was recently presented at the Janeth meeting, is largely that of Maxime Frieden with a little help from his colleague. So we're going to look at a computational model which will be used to correlate with an Air Force Research Lab experiment led by Mike Spotswood and his team. And there's a lot in this model because there's a lot going on physically in the experiment. You have to model the aerodynamics, hence aero. You have to model the thermal field, hence thermal. It turns out there's an acoustic cavity beneath the structure, so we have to model that. And then the elastic part is the elastic structure itself. And we're going to put all that together at some level of modeling and hope for the best. And turns out we did have some success. So here's the model. This is a top view. It's a rectangular plate. Let me again. It's a rectangular plate of length A, width B. We have an incoming flow with certain parameters. We have a pressure on the plate, both steady pressure and dynamic pressure, oscillating pressure due to the oscillating structure. We have a temperature field, and so we need to include all that. And then, oops, need to get out of this. And then if you look at the side view, here's just a cartoon showing the deformation of the structure, but this dotted line indicates there's a cavity, an enclosed volume beneath the plate, and it has its own resonant acoustic frequencies, and sometimes those appear significantly in the total system response. Not always, but they can, particularly if the cavity is relatively shallow, which it often is for practical reasons. And then I'm going to highlight over here on the left a spring, which represents the support flexibility that holds this panel. So the panel is flexible, but what's not always appreciated is the supports are too. They tend to be very rigid with respect to transverse motions, that is motions in the W direction. But if you look at the in-plane motions in the U direction, those are not held rigidly at the supports typically. In fact, it turns out the bending, even of what appears to be initially a massive support, the bending stiffness of the massive support is comparable to the in-plane stiffness of these thin panels, at least in our experience. And we've done some separate experiments directly to verify that. So this mini presentation of this work, we're going to show you some equations of motion. We'll look at the heat equation in particular and say some things about that. We'll talk a bit about the experiment, and then we'll show some results which highlight the sensitivity of the results to in-plane edge stiffness. We'll talk about how we model the heat flux and make an approximation, which has what we think is an acceptable error on the order of 5%. And then we're also going to not only model the structure in terms of its modes, we'll model the temperature field in terms of modes of that field as well. We'll not derive these equations. This is to give you a sense of what they look like if you've never seen them before. And if you're someone like Jack McNamara who has seen them before or something like this, this is just to remind you of what we have in our particular model. So here's the plate equation of motion. Here's the equation of motion with the cavity, and here's the heat equation. So W sub K is the kth mode amplitude for the structure. And so we have a mass, generalized mass, generalized damping, generalized stiffness, the usual linear terms. But now there's a nonlinear plate stiffness associated with the fact that when the plate bends, it also wants to stretch in plane. That gives a cubic stiffness. This is all coupled to the thermal field. It's coupled to the external aerodynamic flow, which we initially used piston theory. It's coupled to the pressure in the cavity. So P sub K is a pressure modal coefficient. And then there's a stack pressure differential. There's a stag pressure differential across the plate as well. So linear plate model, nonlinear stiffness stretching due to bending, coupling to the thermal field, coupling to the external flow, coupling to the cavity aerodynamics or acoustics, and then the stag pressure differential. The cavity equation motion just has inertia and stiffness or inertia and compliance. Again, this comes out of the wave equation for the acoustic cavity, and the acoustic cavity acoustic modes are driven by the acceleration of the plate. And then the heat equation, we have the usual thermal inertia and stiffness, and lots of terms that come from aerodynamic heat. In principle, these terms are nonlinear, but we're going to linearize them, which will substantially simplify our computation. Okay, so that's basically what we're doing in terms of modeling. And again, those are terms that require a little more explanation as we go along. Don't want to go with this in too much detail today, but we're going to take the heat flux. This is not dynamic pressure for those of you who know that terminology. This is the heat flux due to the aerodynamic flow. And we're going to represent it in terms of basically a Taylor series, which is in proportion to what aerodynamicists call the downwash, which is basically representing the motion of the structure as it influences the external flow, and also linear in terms of the wall temperature. And the reason we like this is because this simplifies a molar representation of the thermal field. So now let's talk a little bit about the test case that Mike Spotswood and team did. This is taken from one of their papers. Here's the back side of the elastic panel. It's mounted in a frame, and this frame is relatively massive, but our claim is we think it's still fairly flexible with respect to in-plane restraint, but not, of course, out of plane. Here's their wind tunnel cross section, and in general, they have a shock, and we're doing the case in this situation where the shock is ahead of the panel, so we don't have to worry about the complexity of having the shock on the panel. Okay, and here's just another view, so I won't dwell on that. Here is what happens as the experiment is conducted. This shows you in the bottom picture, we're showing the difference between the temperature of the elastic plate and the support structure as a function of time, as measured. I'll come back to that. And this shows the static pressure on the plate during the startup when it's subsonic, and then goes into a supersonic flow later in the test. And the importance of the temperature differential is that's going to buckle the plate at some point. And then as the delta T goes on, and we reach an equilibrium between the support structure, temperature equilibrium between the support structure and the elastic plate, the plate will stop fluttering due to the fact that it's highly buckled. So let's go on. Okay, so this is the initial computation we did, and we got the right answer for the wrong reason. We made two mistakes, and when you make two mistakes, it's always great if they compensate each other. So when we did this computation, we took a measured temperature on the plate from Mike's experiment, from the AFRL experiment, which was fairly near the edge of the plate. And we assumed rationally, as it turned out, that the temperature on the plate was the same everywhere else, which is not true. We also assumed that the in-plane plate stiffness of the support was very high, which is also not true. But nevertheless, we got what we think is pretty good correlation. So let me tell you why we were initially happy and then later discovered that we were too optimistic. We're plotting the deflection W of this elastic plate at some position on the plate, normalized by its thickness. And that's the relevant ratio for the plate response for something that's clamped on all edges. The deflection is always on the order of the thickness. And applying this versus time. So the tunnel starts up, it's subsonic, and then goes supersonic. And then initially, the temperature differential makes the plate less stiff. And so we go into a flutter oscillation and a limit cycle oscillation. And then the temperature differential gets higher and higher, and the plate, once it's buckled, becomes stiff again. So a plate that's exposed to thermal stress initially will decrease its stiffness, reaches the buckling point, which is sort of a minimum stiffness point, if you will, and then goes back up. So that's why the flutter starts, because of the thermal field, and that's why it stops later on. So initially, we were very happy with that. Okay. No, I won't take time to tell you that story. You can, as a function, well, let me say briefly, as a function of the free stream pressure shown on the vertical axis versus the temperature differential, you can map out where flutter will occur. And then these pink, blue, and black lines are various experimental trajectories through this parameter space. And it would predict, the theory would predict that you go into flutter, come out briefly and then go back in. We don't really see that. And I think that's probably because this is if you will, a snapshot in time that we're doing the computation, whereas the experiment just keeps going, and we probably go through the stable region so quickly that the panel doesn't restabilize. At least that's our current thinking. Okay, now let me show you what happens when we think about this a little bit more. K is a parameter which is essentially the ratio of the in-plane stiffness of the plate to the bending stiffness of the support. And it can vary anywhere from 0 to infinity, depending on whether you have no stiffness in the in-plane support to completely rigid in-plane as well as out of plane. And the results are quite sensitive to this parameter. So if this parameter is 0.5, you see that the experiment is always in red, but the computation is in black. So if this parameter is low, then the response in the theory computation is larger, and it gets smaller as we continue to increase the K value, as in the second lower picture. And then if we increase the K value even more, then the the region over which we see flutter in the computation diminishes. And then if we make it very rigid in plane, as in the bottom picture, effectively the LCO goes away. So what was happening? We didn't like this because basically we knew that the K parameter we thought should be nearer 1 than 1,000. So we started looking at the temperature field, and our model does predict the temperature field. So this shows delta T as predicted versus a distance along the flow direction. And you can see that there's these regions very near the edges where the temperature varies very rapidly. And that's true also in the spanwise direction. So here's the spanwise direction. Again, in the middle of the plate, things are fairly uniform, which is what we'd assume. But the thermocouple that was used to measure the temperature field was fairly near the edge. So our current thinking is that the temperature differential was really probably larger than was measured by the thermocouple near the edge. But we're hoping, and I think Mike plans to do this, we're hoping to get a full field temperature measurement to see if our hypothesis is really right. So anyway, here's our conclusions. We have this model, that's good. We simplified it in a way I didn't go into a lot of detail, but it's important in terms of doing these computations efficiently. The error incurred, we think, is quite modest. The dynamic response of the plate is very sensitive to the assumption made about the in-plane boundary stiffness. So that's something you should measure, we should measure ahead of time. And there are ways to do that. And that has been done for other models. And in the other study, we found good correlation. But we think it was an offsetting, it was a bit lucky. It was an offsetting of two effects which tended to cancel out each other. And now we still get good correlation, but now our physical understanding of why that is so has changed. All right, let me stop about here with some overall conclusions and then invite questions. These conclusions are somewhat philosophical, and various people have said things like this in the past. The best theory is the simplest one that adequately describes a physical phenomena. Of course, it's a search, right? It can be a long search, a long journey to find the model which is as simple as possible, but still adequately describes the physical phenomena. All theories are approximations to reality, but so are experiments. You know, there's the old joke about no one believes the theory except the person who did the computation. Well, everyone believes the experiment except the one who did the experiment. And experiments have their limitations too, at least our experiments do. And I think we always need to be conscious of that. So experiments are not just validating the theory can help you design the experiment and tell you something interesting about what measurements need to be made and what measurements need to be made out of the wind tunnel before you put objects in the wind tunnel, let alone in flight. And then the other thing I would emphasize, and that's implicit in what you've seen, all those models that were vibrating in limit cycles in our wind tunnel, at least, have never failed structurally. Of course, we designed them that way, but the point is you can. And I think that's true of many of the experiments that other people have done as well. That's not to say you don't always fail the model. There's certainly been cases where that happens, but I think the theory is sufficiently well developed that we know how to design models, at least with structural nonlinearities, which will survive the experience of becoming dynamically unstable and then going into a limit cycle. So with that, here's a list of those people who've helped along the way. Not all at Duke, although Danielle Aravi, here is now back at the Technion, but she spent 2 years with us very productively, at least from our perspective, I think from hers as well. Many of you will know Kenneth Hall and Bob Keel, Laurie Virgin, another faculty colleague, and then this is a whole host of people who were once graduate students in our group, with the exception of PC Chen, who's a proud owner of Zona Technology, and are now on well-launched careers elsewhere. So with that, best wishes from our group. And if you have some questions, I would try to answer them. Thank you.